let's now take a look at some photoelectric effect questions. This is a very commonly tested topic, and a lot of the times there'll be ones including experiments and so forth and calculations, as well as some conceptual ones here and there. So we'll be taking a look at a few select questions, starting with this one. So in this particular question, you can see for now, they're giving you a graph, which gives you the maximum KE of the photoelectrons when cathodes of different metals are irradiated with various frequencies of light. As with any graph, make sure you pay attention to the axes. This is a maximum KE, as they've told you. You also need to pay attention to the units. This is in electron volts in this case. And this is the frequency with times 10 to the power 15. So with that in mind, let's look at the first question, which says estimate the threshold frequency for zinc. So zinc is over here. This is the frequency, is the horizontal axis. So you kind of just read that off. It's somewhere between 1 and 1.25, somewhere closer to the 1. So we might be thinking, okay, maybe around 1.1 times 10 to the 15 hertz. So we'll leave that like so for zinc, around 1.1 times 10 to the 15 hertz. Now, state why the gradient of the function lines of each metal are identical. Well, basically because, well, as the frequency increases, the energy of the photon increases according to E equals HF. Therefore, the energy of the photon is proportional to frequency, and therefore you get a straight line relationship. Something along those lines. Now, the next question then says, the lowest frequency at which the photoelectrons are emitted in a metallic cathode in a photoelectric cell is 5.66 times 10 to the 14 hertz. Okay, so we've got a few calculations there. Now, before we do that, I want to head back here and just talk about this particular situation. We may have straight lines, and they all may have the same gradient. And you might recall that often you are taught that the KE max against a frequency is linear, which we clearly see here. You've got the work function identified for potassium there, is the x-axis, and the threshold frequency is your x-intercept, and your work functions are your y-intercepts. Now, often you're taught that the gradient is equal to Planck's constant. But that is only true if KE is in joules. Our KE here is not in joules, so you just need to be quite careful with that, okay? The gradient of this graph would not equal Planck's constant, even though it's a KE against frequency graph, because you need to adjust accordingly. You also need to be very careful. Sometimes this is not KE at all, but an alternative that they could give you is stopping voltage. And again, if it's stopping voltage, you'll need to have to then change the units using W equals QV. Right. Let's do calculations here. So the lowest frequency at which photoelectrons are emitted from a metallic cathode in a photoelectric cell is 5.66 times 10 to the 14 hertz. And he shines a blue laser with a higher frequency onto the cathode. So the incident energy is quite simple. It's E equals HF, which is 6.626 times 10 to the negative 34 times frequency already given. And then you'll get your answer. So 4.19 times 10 to the negative 19 joules. 2 says the work function in joules of the metal. So given that we know the work function can be calculated by H times F0, and you are given the F0, the threshold frequency, You just sub in the numbers. And that gives you your answer again in joules. Which is 3.75 times 10 to the negative 19 joules. And you can see, of course, that the blue light is giving more energy than the amount required. The next question then asks us to calculate the speed of the most energetic photoelectrons. So remember that the Ke max must equal your HF minus phi, both of which we've already worked out. So at this point in time, we'll get an answer of, well, 4. So that's 4.44. So it's 4.4 times 10 to the power of negative 20. This is in joules, of course. And we recognize that this means it's half mv squared equals 4.4 times 10 to the negative 20. So to get v squared, you would multiply this by 2 and divide it by the mass of the electron, which is an answer of 9.75 times 10 to the 10. And of course, v would then need to square root that, which is then 3.12 times 10 to the 5 meters per second. And just as well, just a bit of sanity check. I think a very common mistake is to forget the square root. So don't forget the square root. But a bit of sanity check can also tell you that that answer can't be right. And the reason for that is quite simple. Remember, you can't go faster than the speed of light in simplistic terms. 9.75 times 10 to the 10, if you took that to be velocity, which it isn't, it would be higher than that. So that answer can't be right. In this question here, you're asked to investigate the photoelectric effect. Chromotic light is incident on a metal surface. Mono meaning one, chromatic meaning color, but more sort of technically that means single wavelength. The photocurrent and the maximum Ke of the photoelectrons are measured. Which row of the table correctly shows the change, if any, in the photoelectric current and the maximum Ke of the photoelectrons when the light of the same intensity, the higher frequency, is incident on the same metal surface? Well, the same intensity should mean the same electric photocurrent. So that takes out B and C. The higher frequency should mean it increases, which means A would be your answer. This question, you've got a work function is 4.08 electron volts. Determine the wavelength of light needed to eject an electron from the surface of the aluminium. So the work function equals 4.08 electron volts, which is equivalent to 4.08 times 1.602 times 10 to the negative 19 joules. So it'd be about 6.4 times 10 to the negative 19. But of course, this is going to equal HF0. So your F0 would equal 6.54 times 10 to the negative 19 all over your 6.626 times 10 to the negative 34. Giving you an answer of 9.86 times 10 to the 14 hertz. Now they wanted the wavelength, so don't pick B. That would not be the right unit. It's the right number, but not the right unit. So the wavelength must equal C over F, which is 3 times 10 to the 8, all over 9.86 times 10 to the 14, giving you an answer of 3.04 times 10 to the negative 7, making D your answer. Okay, so the following is a circuit diagram of a photoelectric effect apparatus. Which of the following shows how the current through the photocell varies as the applied voltage is changed? Well, it's definitely not A or D, right? Because as you can see, the voltage is going to change. It's going to, as you increase the voltage, right? You've got it on the cathode, all right? And in this case, remember, the light is meant to be falling on the cathode, okay? That would then give the electron some energy to go over towards the anode. Now, you're applying a negative to the anode, which means you're going to be stopping the electrons. So that essentially means that you expect a graph like B in the sense that when it's negative, you are stopping the electrons. So in other words, this is your V stop. But as you make it more positive, you will approach your saturation current. And so you do have some level of current at V equals 0. So C is incorrect. B here will be your answer. So when light of a certain wavelength, lambda 0, is shone on a metal surface, it is observed that no electrons are emitted. When the intensity of this light is increased, still no electrons are emitted. This shows that light is behaving as a wave. That is not correct. And the reason for that is, if it was, we would expect that as intensity increases, energy increases. But the point is, we still don't have enough energy. And here, having no energy is definitely not correct either. Okay. So here is not behaving as a wave is probably the most accurate. Saying it doesn't transfer energy is probably incorrect either. It may transfer energy in a form that is not an emission of photo electrons. So not behaving as a wave is most consistent with the facts. If we was behaving like a wave, we would expect the energy to go up, but that didn't happen. And so therefore B would be your best answer here. Here at 20, the work function for tungsten is 4.5 electron volts. What's the minimum wavelength of radiating that will have this threshold energy? We've done a very similar question to this before, so you can try this out as an exercise. Now, let's move on to ones that are a bit more, relatively more substantial, or a bit more, not just multiple choice. So here you've got the stopping voltage was measured while varying the frequency of the incident light for an investigation of the photoelectric effect. 3 different metals, A, B, and C, were used, and the results plotted as shown below. Outline the significance of the value of the frequency of light, where the light intercepts the x-axis on the graph for each metal. So we would specifically say that the x-intercepts identify the threshold frequency of each metal. So that is specifically, that is the frequency below which no intensity will result in photo emission or photocurrent. Discuss why the plotted results for all of the metals are parallel. So we would say that the energy of electrons is due to the energy provided by the photons, which have energy E equals HF. Because H is a constant, right? H is a constant. So therefore, the rate of increase in energy against frequency is the same. For all metals. Therefore, they all have, in this case, the energy is in joules. So therefore, the gradient are all equal to H and therefore parallel. So because there's something like that for this question. Okay. So this question here says, the graph shows the maximum Ke with which electrons are emitted as a function of frequency for two different metals, X and Y. The metals are illuminated with a lighter wavelength of 300 nanometers. What would be the effect of doubling the intensity of this light without changing the wavelength? Well, in general, we would say if the intensity goes up, then the photocurrent would go up, but the Ke would be unchanged. That's what your theory tells you. Okay. And so taking a look at this, we might say, well, I mean, you know, you might be thinking X and Y, they're both metals. They're both going to be subject to the same thing. And so you might be thinking, okay, there's really no difference between X and Y here. And then you may think that, well, photocurrent goes up, K unchanged. So definitely not C, because that's the wrong thing, right? Because it's telling you photoelectrons emitted would not change, but would increase. This is if frequency of the incident light went up, but that's not what's happening. We're increasing intensity. And so you might think it might be D. And I think many students would leave it at that. But here's the thing. There's something we haven't really considered. And so it may be D, but there is the fact that these metals are illuminated with a light of wavelength 300 nanometers. And we haven't used that information yet. So let's just check this out, right? If the wavelength is 300 nanometers, then we can calculate what the frequency is. Well, I guess that's 1 times 10 to the 15 hertz. Or in other words, it's 10 times 10 to the 15 hertz. In other words, we're emitting the light here at that frequency. Now, if we're emitting it at that frequency, we'll note that this frequency that we're emitting it at is less than the threshold frequency for Y. But it's greater than the threshold frequency for X. In other words, for Y, nothing's going to happen It doesn't matter what the intensity you do. So that means for y, because the light's here and the y's F0 is here, then you're not going to get any photoelectrons, no matter what the intensity is. And so I guess if you were to double the intensity, it's not really going to change anything for y. So when you say the number of photoelectrons emitted will increase for y, that's not actually accurate. Because for y, it's going to be 0 on both occasions. So the better answer would be that for metal X, the number of photons emitted would increase, but the maximum Ke would remain unchanged. Of course, A is wrong because that's an increasing of frequency. A and C are wrong because that's talking about increasing frequency. D is actually wrong in the sense that, well, for Y, it's going to be 0 in both. So the amount of photoelectrons would actually not increase because the threshold frequency is not met. So just be careful with that. If they give you information in a question, it might be a good idea to think about how that may be relevant or how it may change the question. Here we have this question. A laser emits a 1 watt beam of blue light with a wavelength of 425 nanometers. Calculate the number of photons which are required to transfer 5.5 times 10 to the negative 4 joules of energy. Well, we know each photon has energy E equals HF. And we know F equals C over lambda. So that's going to be 4.68 times 10 to the negative 19 joules per photon. But the question is asking about the number of photons required to transfer 5.5 times 10 to the negative 4. So the number of photons, of course, would equal the energy required over energy per photon, which is 5.5 times 10 to the negative 4 divided by 4.68 times 10 to the negative 19. And that you can probably see is going to be a reasonably large number, giving us an answer of 1.18 times 10 to the power of 15 photons. B then says, if the laser is shone on the surface of a potassium plate with a work function of 2.29 electron volt, calculate the maximum Ke of the photoelectrons. Okay. So we know Ke max must equal HF minus phi. HF we've already worked out, so let's not do it again. It's 4.68 times 10 to the negative 19. Now phi is 2.29 electron volts. But we've got it in joules before, so we need to change that into joules. And see what that gets us. That gives us about 1.01 times 10 to the negative 19 joules for the Ke max. With reference to the particle model light, contrast the 1 watt beam of blue light and a 1 watt beam of red light. So for 2 marks, we basically need to then compare this 1 watt beam and 1 watt beam. And we basically need to say, I think, 2 critical things. Essentially, let's make this a bit bigger. Essentially, we'd say a few key things, all right? So the key things we'd say are the blue light would be composed of photons that have shorter wavelength, higher frequency, and therefore more energetic. The red light would be composed of photons that are less energetic. So I think that's really the key thing, that number one, you need to say the photons would have different energies, i.e. E equals HF, F is different, so different F, different E. Essentially. But it's worth 2 marks. There's going to be something else that you're going to have to say as well. And the important thing to recognize is that they're both 1 watt. Now, watt, remember, is a unit of power. This is power, which is energy over time. If we're going to be giving out photons with less energy for the red light, how can it possibly have the same power? So we would say that while the red light has photons that are less energetic per photon, the red light provides more photons per unit of time. It emits photons at a greater rate compared to the blue light to maintain the same power output. So you can think of it as perhaps the red light is a bit brighter or a bit more intense compared to the 1 watt blue light. Those are the 2 key things you need to say. One, basically, the blue light would have photons that are more energetic relative to the red light. However, it will give out less photons per unit time. The rate of photon emission will be lower. So it would be less bright or less intense. So taking a look at this question here. In a photoelectric experiment using the apparatus shown below, the stopping voltage for light of a given frequency was measured. When the wavelength of light hitting the photosensitive metal was 4.5 times 10 to the negative 7 meters, the stopping voltage was 1.14 volts. What is the work function of the metal? Okay. So understand here that you've got the wavelength. Written down. And from this, you can get the frequency. Okay. So we'll get 3 times 10 to the 8 divided by 4.5 times 10 to the negative 7. And this gives us an answer of 6.67 times 10 to the 14 hertz. Now, this, of course, will then provide energy of E equals HF, which we can work out. And that's 4.42 times 10 to the negative 19 joules. Okay, so we've got enough energy there. That's what's hitting it. Now, once that hits it, you're going to then need to have take away the work function. And then the work function will have, so your KE max equals the energy we just worked out minus the work function. Now, the stopping voltage here help us work out KE max, because KE max must equal Q times V. So that's 1.602, the charge of the electron, times 10 to the negative 19, times 1.14. And that gives us an answer of 1.83 times 10 to the negative 19 joules. Of course, we can work out that rearrange phi must equal HF minus KE. So that would be, using the numbers we already worked out, 2.59 times 10 to the negative 19 joules, which would make B here, your answer. And so that's basically how you approach all the different photoelectric questions. You can see you need to understand E equals HF very well. You need to understand the relationships well, the idea of threshold frequency and your equations well. Make sure you know your graphical and all your units well, because I do try to mix them up every now and then. But if you take care of all of those, then photoelectric questions are quite common, but also very doable. And basically, that's how you do the questions.